Okay, good morning. Here we go. We're going to see how far we get through electrostatics. I mean, there's only 8 lessons, but there's only 2 weeks left of school. So we'll see how this goes. Yeah, so electrostatics, often this is at least introduced in what used to be grade 9. I'm not sure how often it shows up anymore anywhere throughout the curriculum. So yeah, we'll see how this clicks with you guys. So here we go. Electric charge. As you guys know, this isn't particularly earth-shattering, but matter is made up of atoms. We've got the nucleus, we've got orbiting electrons. You would have seen this all over science, grade 9, grade 10. These orbiting electrons, we give a notation to. I don't know if you've seen it before, but we generally give it the notation of E minus. And then in the nucleus does not move, well, in matter at least, unless you make the matter move. You've got protons and neutrons. Now, again, don't know if you've seen this notation before, but generally we call the protons P plus, and the neutrons are just N 0 because they have no charge. These two have a large mass compared to electrons, which is important to electrons. So when atoms bond together to form solids, excuse me, the electrons can be tightly bound to the atoms, as in a covalent solid like glass. What that means is if they're tightly bound to the atoms, the electrons don't move easily. And if the electrons don't move easily, you get an insulator. But there are some types of materials where the electrons are free to move, as in metals. If the electrons are free to move around, these materials are called conductors. The electrons can move easily. So subatomic particles like protons, neutrons, and electrons have a property known as charge. You are aware of this already. It is charge that is responsible for electricity and magnetism. Magnetism we won't get to, unfortunately. But believe it or not, it's the charge on these atoms that is responsible for magnetism, which is pretty cool. There are 2 types of charge. We call one positive, we call the other negative. Charge is measured in units. It has units. I don't know if you've ever talked about them in a previous course, but that unit is called the coulomb, named after a French physicist. And charge is represented by the letter Q. So there's big Q and there's little q. Both of them are used. And we say that 1 Q of charge, so 1 Q is equal to 1.6 times 10 to the negative 19 coulombs. So, Q being total charge, and then this 1.6 times 10 to the negative 19 we call the elementary charge. So this is actually the charge, the amount of electrical charge on like an electron, for example. This is why. So we took this number, and to simplify the mathematics here a little bit, we just said, well, this is just 1 Q. So another important fact about the charge is that it is quantized, which is why having a variable like Q makes sense. You can only these things only come in certain sized blocks. You can't have partial amounts of charge. So this means simply that the charge is like money. With money, there is a smallest unit, the cent, and any amount of money can be broken down into a certain whole number of pennies, which we used to have but don't anymore. But never a fraction of a penny. Like you can't split it down even further when you're dealing with change. So the smallest unit there is the cent. And any larger amount, so they're just using money here, a larger amount of dollars is just some integer multiple of a single cent. or not an integer multiple, but some multiples of cents. With respect to charge, the smallest unit of charge is called the elementary or fundamental charge. This is the amount of charge on a proton or an electron. This is given to you by the letter E, and it is 1.6 times 10 to the negative 19 coulombs. And then all larger charges are a multiple of E. So we'd say if you have some charge Q, this is going to be some multiple, integer multiple, and I was wrong, yeah, this is an integer multiple of E. So we know we're multiplying in there. So by way of a technical comment, some of you may actually be aware that there are particles that have fractional charges. We're not going to deal with those. They have actually, there's a 2/3 charge and a 1/3 charge. So E is not actually the smallest absolute charge, but for the stuff that we're going to be looking at, that's not relevant or important. But it does exist. So just by way of some examples here, we want to find the, if we were asked to find the number of fundamental charges in a particle of charge, this 2.5 microcoulombs, just to jog your memory, a micro, anything micro, is 10 to the negative 6. Nano, because it might be useful, is 10 to the negative 9. And sometimes we go the other way and we use a little m. M is milli when we're using it as a prefix, and so that's going to be 10 to the negative 3. So if we wanted to know how many elementary charges, so how many electrons or protons would I have to put together to give me one blob of charge that has a total charge of 2.5 microcoulombs, we would just use this relatively simple equation here, where we have total charge is equal to an integer multiple of elementary charges. We're told that the total number of charge is 2.5 microcoulombs, so I've got 2.5 times 10 to the negative 6 is equal to some integer multiple of 1.6 times 10 to the negative 19. So you divide by this, and we're going to find out. So divide by 1.6 times 10 to the negative 19. And we get that n, the number of elementary charges, in this case, is 1.56 times 10 to the 13. And since this charge here is positive, this has to be the number of protons. So there is a large number of protons in our mass that has a charge of 2.5 microcoulombs. I think it seems relatively straightforward, but there's a lot of interesting results that flow out of this. So it should be on your data page. If I flip back to the front of my book, we've got some up to this point here. These constants were used for gravity. These constants down here are going to be used for electricity and magnetism. So K we'll get to in a sec. The elementary charge you don't have to remember. It's given to you here. 1.6 times 10 to the negative 19 coulombs. We got the mass of the proton, mass of the neutron, mass of the electron. You can see that protons and neutrons are very similar in mass. Electrons are much, much lighter. And we'll get to what mu naught and K are here in a bit. So we've got the elementary charges here listed as well. Elementary charge, electron mass, proton mass, neutron mass. The data page does not explicitly list the charges of the particles, so you got to remember that electrons are negative. So an electron would have a charge of negative 1.6 times 10 to the negative 19, and a proton would be positive 1.6 times 10 to the negative 19, and a neutron would have no charge. It used to show up in Science 10 when you talked about radioactivity, but I think that's no longer part of the curriculum. There's a particular type of particle that they didn't really know what it was, and so they just called it an alpha particle. What they discovered later is that an alpha particle is actually a helium nucleus. And a helium nucleus contains... Sorry for the interruption. Here we go. Helium nucleus containing 2 protons, 2 neutrons. That's what they discovered an alpha particle was. Connected to alpha radiation which you may or may not have talked about in Science 10. So what is the charge of that particle? We know that Q is the number of elementary charges times the elementary charge, and we know that there are 2 protons, 2 neutrons. Neutrons have no charge, so this is going to be 2 times positive 1.6 times 10 to the negative 19, and so that's just going to give us a charge on a helium nucleus of 3.2 times 10 to the negative 19. The charge is measured in coulombs. So if we're doing electricity and magnetism experiments on a piece of matter, then we need to note that it is only the electrons in that piece that can move. The positive nuclei are fixed in place by the chemical bonds in that object. So for a conductor, the electrons flow freely. For an insulator, they do not. If you guys are here in class, I'd have all sorts of stuff that I can use to show you this, but right now all I've got is pictures. So you've got a negative rod here brought close to an insulating ball. So if this thing's negatively charged, so we can see, I'll just put them in here too. These guys will represent the protons in the nucleus. Well, the nuclei are positive. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This, yeah, representing the atoms that parts of the atoms that cannot move. They'll just kind of sit here. And so if we tell you, I'm going to use green, if we tell you that this rod is negative, what that means is there have to be more electrons on the rod than there are protons. So I'm just going to toss a whole bunch of these guys in here. You can see that that thing is negative. And so as we bring it close to a ball, what we would see if I were to actually do this for you is that the ball is first attracted to and then repelled by the rod. We want to look at why that is. So if we got this ball here, this ball is, there's going to be 1 positive, 1 negative. What you're going to have here is if this is overwhelmingly negative and this is positive, what you should remember from elementary school or middle school, wherever you looked at this, is that these objects, because this one's negative and this one's neutral, these 2 objects are going to attract. So this guy is going to swing over. What happens here is all of these negatives, the power of these negatives cause negatives to repel. And so what you get here is that you get a positive, this needs to be pink. The proton that can't move stays where it is, and the electron, the 1 electron that this ball had, goes over to the other side. And so you get the positive, it gets pushed away, and so you get the positive proton that's left on this, kind of in the center of the ball, gets dragged towards this excess negative. What's going to happen here is as we've got the positive in the middle and this negative on the outside, some of these excess negatives, these electrons are going to repel each other. So the excess negative charge on here, some of it is going to transfer. There's going to be a transfer electrons because the electrons here are going to repel each other. And so then what you're going to get here is you're going to have electrons, but as these guys transfer over here, you had that 1 positive. But now instead of just having 1 negative, maybe we have 1, 2, 3, 4 negatives that kind of disperse themselves around. And so it's this transfer of electrons throughout the course of the experiment that determines how this happens. This thing right here, where we have a negative object brought to a neutral object, and the electrons in the neutral object move to one side, this is called polarization. If you've taken chemistry, you should recognize this term. Polarization is where one side of an object or part of an object is positive while another part is negative. But the entire object is neutral. So when you're looking at things like water molecules, there's a dipole there where the oxygens are more negative, or the oxygen is more negative, the hydrogens are more positive, because the electronegativity of the oxygen, I believe, is greater, if I'm remembering that properly, from chemistry. So you get the same sort of effect. You can induce that same sort of effect in other neutral objects just by bringing charged objects towards them. And then once we get down here, we see that the two, now that these are both negative, they repel each other. We see that phenomenon in this apparatus here. I'm going to post a video of this apparatus actually working. This is called a electroscope. Sometimes it's called a foil leaf or a gold foil electroscope or a gold leaf electroscope. There's a bunch of different names for it. They all mean basically the same thing. What you've got here is this object here is insulated, so it's not touching anything. It's not touching anything electrically conductive, and it goes into this box. These two leaves at the bottom can swing freely, or some of the electroscopes have one rod that is rigid and the other one is a leaf that can kind of swing off. And generally speaking, when this is the way it is, this whole thing is neutral. And so what I'm going to do here is I'm going to draw in some protons. 1, 2, 3, 4, 5. And then this leaf and this leaf each have 2 protons, but the whole thing is neutral, so I need the same amount of electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going to have an electron just to kind of balance off all of these. There. Now for each one of these, I'm going to draw the protons in the same spots. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Because the protons can't move. It's only the electrons that can move, so those have to stay in the same spots. So when a negative rod is brought close to a gold foil electroscope, let's see what happens here. If I have a whole bunch of negatives on here, what these negatives are going to do, and I'll zoom this in, maybe it'll be easier to see. What these negatives actually end up doing is they repel the electrons that are at the top of the electroscope. And so this guy wants to get away. And so what ends up happening is as this guy gets repelled, it starts to repel all these guys. And so you end up with a bunch of electrons stacked up on these 2 leaves. That gives these 2 leaves a negative charge. And so then these 2 leaves swing apart and repel each other. So these negatives are going to push all the 1, 2, 3, 4, add 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so the electrons are all going to make their way down to get away from this excess negative. And these foil leaves are going to, or the negative charges now are going to force these 2 guys apart. When you take away that rod, the electrons are going to redistribute themselves. Because now this end is really positive. There's a ton of negative down here. So the electrons are going to be attracted back to this end of the electroscope, and they're going to repel each other. So you want the electrons are going to flow back up. I want to post a little video about this. It's got some lovely music in it. I'll attach that to this lesson as well. This is something I would do if we were all together. I'm going to do 2 lessons here right away in this video. So the first set of problems I want you to look at here is, they're simple. It's just basic calculations using Coulomb. So I want you to do 1, A to C. I want you to do 2, A to C. And then I want you to do 3 and 4. Ooh, and 8. 8's a good question. It involves equilibrium and tension using the force from a charged object. It's quite cool. So take a look at that. And we're going to jump ahead here.